Hello and welcome to my CIS6035 development project presentation. In this presentation, I'm going to briefly introduce the development project, the planning phase, the development phase, testing and deployment. It's going to go over the key points, key elements of the project itself. There'll also be a short demonstration of the application I have developed. So the application itself is a Chrome extension that uses TensorFlow.js, the machine modeling language, to allow a user to scan a URL in their browser, and it will give them a confidence report on whether the URL itself is malicious or not. Firstly, when designing this project, there has to be some form of planning and frameworking involved to get a general idea of how the system works and interacts. So this is sort of the beginning of the planning phase. You can see here that I've developed a very small data flow diagram, very simple, basic, just to give a general idea of how the different modules in the system interact. You can see the different modules in the squares sort of represent the different aspects of the Chrome extension and the machine learning model itself. And between each of the modules, you can see the sort of the data flow, what happens, how they interact with each other, and then eventually give the user a confidence report on their browser itself. So before we go into how we eventually implemented that design and that framework, we have to start at the beginning, where we have to initially find the data itself that we're going to train the model on. The data itself comes from Kaggle, which is a reliable source with user ratings on the usability and completeness of datasets. So this dataset that I'm actually using has the highest score possible for usability, which just goes to show how good the dataset actually is. So initially the data is actually going to be pre-processed, it's going to be normalized as well for the model itself to learn on. And we're going to use some basic machine learning libraries such as scikit-learn, matplotlib, pandas and numpy. We're going to do a bit of feature extraction, sort of just get a general sense of how good the data set is and how usable it is, just to show the broadness of the different features that are involved in all the URLs, so they're not all the same, because that'll limit the actual learning of the machine and the overall accuracy of the model itself. So let's dive into the feature extraction analysis involved in the dataset. So later on, I'm going to explain why this feature extraction is quite important for the tokenization, how that links. It's going to be an example of how maybe the Keras model itself uses the tokenization to break the URLs down and then feed it into the machine learning model itself. But here we're just spreading the features out and just having a look at using a heat map, how the distribution of the features across the data set. So you can see that it's quite a broad feature set that we've identified, which again goes hand in hand with the usability of the data set itself. And then we can go into feature extraction and analysis in a little bit more detail. So I've got three graphs here, each of them displaying different features and sort of their presence in the dataset itself. First one goes into abnormal URLs, which is basically the presence of a network location in the URL multiple times, which is a good sign of whether the URL is malicious or not. So that's a heavily represented feature in the data set, which is good. But then we do also have two graphs here that depict two features that are relevant to whether a URL is malicious or not, which are very heavily underrepresented in the data set. So this is important because it gives a good sense of the features that are sort of required in determining if a URL is malicious or not, but it also shows how they are represented in the feature set and the data set, which give an example of the variance of the data, which is good for the model itself, but also shows the limitations of how the model can learn. So the model's not going to learn a lot from very few cases of having an IP address, for example, or secure HTTP, as these two graphs on the right show. But it will also, the model itself will train a lot on the presence of a network location multiple times in the URL, as depicted in the left graph. So after we do a bit of feature extraction, feature analysis, we're going to normalize the data a little bit. All we did was make the label 0 for benign, 1 for malicious, make it a binary classification problem. So for binary classification, sequential and a sigmoid was basically the best model to use for this problem. Other parameters, other models were tested, but we found that this combination gave us the best results. And we also added an LSTM layer as well for the dropout, the recurrent dropout, just to reduce the overfitting of the data itself. So different parameters were tested in the model definition, as you can see here. Different activation functions were tested as well. Different parameters on the layers were tested, but these parameters you can see here were the best ones that gave us the best results, best accuracy and lowest loss metric. When testing, though, we did come across a few limitations, a few errors when for the hardware itself that we tested the model on. The processing was quite slow and was peaking out at 100%. So this sort of gave us a few limitations for actually training the model itself. But after we increased the epochs and decreased the batch size, it actually allowed the hardware to handle the testing quite effectively, quite efficiently. So once the model parameters were finally decided upon, the model itself was tested with about 20% of the data set itself. I was going to say 0.2. So after the model was tested on the training set, on the testing set, sorry, it was then decided that the parameters that we had so far were going to be deployed on the extension itself. So the model, the Keras model that this was initially developed in, had to be converted to a TensorFlow.js model, which can then in turn be used on a browser on the client side without having to have any server-side code to be run. So the model just goes through basic conversion that was then done in Google Collaboratory with just some basic command line instructions, which then just convert the model to a TF.js or TensorFlow.js layers model, which can then be called in the Chrome extension. So after the model has been converted to a TF.js layers model, it can then be called into the actual extension itself. So here you can see the manifest.json file here, which is basically it defines the parameters, the permissions, and what files need to be loaded into the actual extension itself. The extension is going to be debugged and tested in Google Extension Developer environment, which just allows you to deploy the extension itself as an unpacked extension. Basically, just lets you play around with the extension as if it was deployed in the extension store. So important files to take note of here are the manifest.json, so I've described, the content, background, and pop-up JavaScript files, which all interact differently with the user's browser. The GoFish HTML file, which then just displays the confidence report to the user, and the actual JSON GoFish model, the actual machine learning model itself. After we do the Chrome extension development, we can then do a little bit of testing. So we can deploy the extension unpacked in Chrome, and then we can actually use the extension itself locally and test the model or test the whole extension on real-life URLs. So we're going to test on about 180 URLs. 113 of them are going to be benign, and 67 of them are going to be malicious. This ratio was determined after doing a bit of research and finding a bit of data on the sort of amount of benign URLs to malicious URLs between 2022 and 2023. So when we tested the extension itself on the 180 URLs, we found that there was about a 74.6% accuracy on the malicious ones and 90.28% accuracy on the benign ones. Now, these malicious URLs are realistic and are located on URL House, which I will then demonstrate later on the actual demonstration of the project itself. But these accuracies sort of show that there's a little bit of inaccuracy, which can be attributed to the fact that the dataset is a little bit outdated. The features themselves in the dataset are very realistic and very reliable and good for the model itself to train on, but are a little bit outdated on up-to-date, realistic, malicious URLs that they were tested on. It can be said that maybe the testing data, the realistic testing data, is a little bit limited, might have features that weren't located in the tokenizer or the sequential model itself. But we'll go on to the improvements that can be made in the next slide. And so we can go into the improvements and recommendations. So going forward, in the future, the Keras model itself can in fact be directly coded and developed in a JavaScript environment in the browser itself. This could improve the effectiveness and the efficiency. Data's not being collected on this, so there's no definitive answer, there's no definitive metric to say that it's better or worse, but it's something that could be recommended for the future. Something that definitely can improve the model itself is training the model, the Keras model, on up-to-date malicious URLs, as defined in the previous slide. Having modern, up-to-date URLs trained in the Keras model will 100% improve the accuracy on realistic URLs that are going to be scattered across the internet, which is obviously depicted in the testing phase, as you saw. Something that could be a recommendation / improvement on the actual extension itself is the ability to scan the whole web page of URLs and give sort of a recommendation score on each of the URLs as you maybe hover over URL, or just have a list of the URLs that you do not want to touch on the site. So something that can be improved in the Chrome extension itself. Instead of having a user intervention that could slow down or just prove tedious for the user, it can just be automated, so it's easier to define and identify the malicious URLs. So now we're going to go on to just a quick demonstration of how the actual Chrome extension works in the user's browser.
So as you can see here, we have the extension itself unpacked and deployed in the Chrome extension tab. It's added on the shortcut so you can quickly access it. And as a demonstration of how it works is we go to URL house. This website is where we tested all the malicious URLs for the testing phase of the model itself. All of these URLs are verified malicious URLs, and so it's going to give us a high confidence output. The output itself will be because it's binary classification, will give us an output between 0 and 1. Lower and 0 will be it's a benign URL, and 1 is a definitive malicious URL. So the threshold that I had defined was anything over 0.75 would be a malicious URL. And for an example, if we choose any of these malicious URLs, we right click and we select the scan, or the menu context menu item to scan the URL. It will then get fed into the machine learning algorithm, into the extension itself, and if we go up here we can see the confidence output, or the output of the machine learning algorithm gives us a result of 0.854, which is very high and indicates that the URL that you just scanned is a malicious URL.